Great, thanks Jamie, and thanks everyone for joining. I can't see anyone's faces while I'm sharing my screen, but please do speak up if you have any questions or something's gone wrong as I present. So today I'm going to talk about ecological forecasting for resource management during climate extremes. And a lot of the work and the case studies I'm going to present on were actually done during a research position where I was based in California with NOAA Fisheries, but I've, as Jamie was saying, I've since kind of moved back to Australia where I have a position at CSIRO. So society is increasingly facing novel and uncertain environmental conditions as a result of climate change. And these changes to our Earth's climate at the physical level is starting to kind of cascade down to our ecosystems. And this is resulting in unprecedented impacts, from species changing their distributions to unwanted fisheries bycatch and entanglement and declining ocean health. And so these climate extremes pose a huge challenge for marine management. And to really understand and predict for these changes, we ultimately need accurate predictions and forecasts, and we need those across all forecast horizons. But when we think about forecasting into the future, then it's important to consider that decisions change across timescales. So at shorter timescales, we might be thinking about how fishing, for example, might be impacted by the weather. As we move forward in time, at seasonal timescales, we might think about when to harvest or to hire labour. And then as we move further out, we're thinking more kind of on strategic timelines of rebuilding stocks, implementing spatial management plans, and long-term planning and kind of climate resilience as we move out to that century timescale. And so there's a really strong argument that forecasts at these intermediate seasonal to annual timescales are most important to resource management, who are faced right now with increased uncertainty from climate change, from climate extremes, I should say. But forecasting ecology at any of these forecast horizons ultimately relies on ecology being predictable. And that kind of begs the question of, where does ecological predictability come from? And so in the ocean, it can come from life history traits from various species. So for example, long-lived, large and high trophic level species generally have greater predictability for population forecasts. Ecosystem persistence also gives us predictability. So this is the idea that the ocean tomorrow looks a lot like the ocean today. We get predictability from animal phenology, so thinking about animals that migrate every year, like whales. Passive advection from animals that are pushed around on ocean currents. And we also get predictability from animal responses to environmental conditions. And so this is a lot of where my research is based, looking at species distributions and the environmental kind of variables that drive where they're found. And so because ecological predictability comes from so many sources, it gives us a range of options for how we can actually set up a forecasting system. So for example, we have forecasts or ecological forecasts that rely only on the forecast of the physical environment. And this is an example of a temperature observations being used to predict lobster migrations. We can use just purely ecological observations, so thinking about autoaggressive traits or life history traits that can predict population changes or species shifts. And then I think probably most commonly, and a lot we hear about in the ecological forecasting space, is when we couple ecology with the physical forecast system. And so one example that the Oceania group has probably heard about is the timing of tuna migrations in the Great Australia Bight. And so this kind of option C here is really important, because when we use and kind of rely on these forecast fields from initialized Earth system models, we can get a better handle on unprecedented change. We're not kind of relying on what has happened in the past to predict the future, but we're kind of being prepared for how uncertain the future actually is. And so there's a range of ecological forecasts already operational. These are some particular NOAA examples from the US, so things like Coral Reef Watch, forecasting pathogen risk for shellfish, harmful algal blooms, out to marine heat waves. And they're kind of at the physical level, but there's also operational ecological forecasts at these similar kind of seasonal forecasting timescales. And these are just NOAA examples of looking at minimising bycatch, forecasting salmon returns, and forecasting catch limits for fisheries. As we kind of move out into the next kind of chunk of the forecast horizon, moving from a year to multiple years out to the decade, this is kind of the next frontier for ecological forecasting. But we already have a few examples from kind of forecasting tuna catch, chlorophyll A, primary productivity, and even fish habitat out to 10 years in advance. And so these are some really amazing tools that are already operational in many instances. And so when we kind of were faced with this and thinking about what are some additional tools that we can develop, we were really interested in relying on existing management tools. So resource managers already have a lot of tools that they use to manage fisheries and bycatch problems. And so we wanted to see if these kind of historical or real-time tools can actually be transitioned to a forecast configuration. And so to test that, we did some work where we picked a few management tools that are currently used off the west coast of the US. And we actually looked at the area that they operate in, the variables that are used in management, and the kind of time in which that management tool is typically implemented. And we just looked at the skill of the physical forecasts for that kind of space, time, and variables. And so this is a kind of list of the tools here. The details don't really matter here, just more that we have multiple tools. And this is the anomaly correlation coefficients for those tools. And so what we can see is that there's kind of some tools that are already kind of predisposed to likely having higher skill than others. And so we zoomed in on that a little bit and we said, let's actually pick two of these tools and transition them to a forecast and see how they perform. And so these are the kind of two case studies that I'll step through today. The first is a tool that examines sea turtle bycatch in a drift gillnet fishery that targets swordfish. And the second is what we call the habitat compression index. And this is talking about whale entanglement off the west coast of the US. Okay, so the first case study that I'll explain a little bit is all about crabs, whales, and climate change. And so off the west coast of the US, and specifically off California, we have environmental change, for example, marine heat wave, but this can represent any kind of environmental variability. In this system, marine heat waves can actually drive whales inshore, and this creates this increased overlap with fishing vessels that are using crab pots to target Dungeness crabs. When we have this kind of increased overlap between whales and boats, we have high entanglements, and that actually leads to a number of fishery closures to try and reduce those number of entanglements. And so in this system, these kind of fishery closures are really, really effective at saving whales, but it does come at a large socioeconomic cost for the fishery. And so this metric was developed to help management understand what was going on and what was driving whales inshore. And so whales like to forage in nutrient-rich upwelled water off the California current, which is an upwelling system. And so upwelled water is actually can be very simply characterized by being cold. So if you just simply look at the area of sea surface temperature that's colder, you can identify the area of upwelled water. So here in 2013, we can kind of see this large patch of cool blue water, and that's the upwelled water for that 1 month in May 2013. In 2016, there was a really large marine heat wave that moved into the area, and you can see here this kind of like warm red water pushing in, and it's really compressing that cool upwelled water along the coast. And that compression of that optimal whale foraging habitat results in a higher density of whales overlapping with the fishery. And so if you simply measure the area of upwelled water, you can decompose it into a time series. And this kind of metric is what we call the habitat compression index. So it's measuring that amount of upwelled water along the coast. And so when you have any values below the long-term mean of compression, which is highlighted here in red, you have really high entanglement risk for whales. And so because this metric is already used in management, it's used in kind of a real-time way, instead of using kind of observed sea surface temperatures, we thought, why don't we actually try using forecast sea surface temperatures and test whether we have any skill? And so that's what we did. And we used the global sea surface temperature forecasts from the North American Multi-Model Ensemble. And that's 6 global forecast models that are served. Each of them have a number of ensemble members. So this actually gives us 73 different global sea surface temperature forecasts that were used to kind of predict whale compression events. And this is what an example forecast looks like. So this is the same time series as before, but we've just zoomed into a smaller period of time from 2013 to 2017. And this kind of large grey block indicates the area that a very large marine heat wave kind of moved into the area and resulted in high habitat compression. And that was observed, and that's shown by the black line here. So as the black line kind of dips below its horizontal threshold, we have high habitat compression. And the coloured lines here represent 3 example forecasts, 1 month, 7 months, and 12 months into the future. And so what we're seeing is those coloured lines, when they dip below the kind of horizontal threshold, we're having we've correctly predicted a high habitat compression. And so this is really showing that during this marine heat wave, we had up to a year advanced warning. We could have had a year of advanced warning if we had a forecast system in place. And so this is just a time series, but we wanted to kind of test our skill more explicitly. So we did a retrospective forecast skill assessment based on every month from 1981 to 2020. And so this is the idea that for every month, we generate a forecast for 12 months lead time. For each of those forecasts across all of those years, we looked at 3 metrics of skill. One was just a simple correlation coefficient. And because we're kind of using annual data, we accounted for autocorrelation when we're calculating that. The other 2 metrics kind of rely on this confusion matrix style here, where we kind of count the number of events that we correctly forecasted and the number of events that we got wrong with our forecasts relative to the observed. And from that, we can calculate forecast accuracy, which is just the fraction of correct forecasts. We can also calculate SETI, which is the Symmetric Extremal Dependence Index. And it's doing something similar, but it's really, it does a really good job of taking into account that these are typically rare events. You know, these climate extremes are rare events. So when we look at the results of that retrospective forecast experiment, we have the correlation coefficient shown here on the left, and we have the correlation between observed and forecast compression events for each month of the year on the x-axis and for each 12 months lead time for the forecasts. So every time you see a black dot on those boxes, it's statistically significant. So what this kind of means is that for each forecast month, at lead times 4 months into the future, we actually have really good skill of being able to predict high compression events. And in fact, during winter and spring in North America, we have up to 12 months skill in being able to predict those high compression events. And that time of year is actually really ideal for management that are making their decisions around that time. And so this is just one metric, but these results are kind of consistent across those 3 metrics that we see. So this is kind of forecast accuracy here, where anything in red is showing us good accuracy, and SETI here, and again, anything in red is showing really strong skill. Okay, So what does that mean for management? You know, how could management actually use these forecasts? Because we've just demonstrated that we have really good skill in being able to predict these high compression events. And so there's a number of potential actions that management can take during these high risk compression events. The fishery is actually kind of divided up into these 6 different kind of spatial zones, depending on the information that they want to deliver in terms of the time of the month that the fleet operates, and the time of the month that the whales are foraging, because that's often has variability associated with it. And so what we kind of see is that these actions of advising fleets on when there's high risk conditions, or advising fleets on potential fishery closures are 2 really good actions that these forecasts could help with in forming those decisions and communications with the broader kind of stakeholder group that's involved in this fishery and its management actions. Okay, so the next case study is quite similar. It's loggerheads in hot water. So loggerhead sea turtles typically live off Baja California, this kind of long peninsula down here. But when we have El Nino events, marine heat waves, this kind of natural variability in the system that can be quite extreme, these turtles actually extend their distribution further north, where they overlap with a swordfish drift gillnet fishery. And when that happens, there's a fishery closure to avoid bycatch of these turtles. And so this is, again, an existing management tool that we already have in this area, where we use the 6-monthly kind of running mean temperature anomalies in this box of Southern California. And when those temperatures exceed a threshold indicated by this red line, we have this kind of a potential fishery closure, because this is when we have high loggerheads in the area. And so again, we have, you know, this really nice sea surface temperature anomaly time series. And instead of using observed sea surface temperature, we substituted that with forecast temperatures from those 73 different forecasts. And this is an example forecast at the top here. And it's again for that critical kind of marine heat wave period where we saw this kind of unprecedented warming of the California current. The black line is showing our observed sea surface temperature anomaly. And when, in this case, when it exceeds that horizontal threshold, we have a fishing closure. And our coloured lines are representing forecasts 7, 9, and 12 months into the future. And again, you can kind of see when those coloured lines are exceeding their horizontal threshold, we're accurately predicting that fishing closure. And when we run the retrospective kind of forecast experiment, these are the kind of skill plots down the bottom here. The fishery closure is only enacted during 3 months of the year, which is why we only have 3 months on the x-axis. But for the kind of every lead time, 6 months into the future, we have good skill for the correlation coefficients, forecast accuracy, and SETI. So we were really encouraged by these results, and those results were using the global sea surface temperature forecasts that are served by the NMME, and they are quite coarse resolution. They're served once per month. They only serve monthly sea surface temperatures, and at a spatial resolution of 1 degree, which is quite coarse, but there are 73 ensemble members. And so we actually wanted to test what is the benefit of dynamical downscaling. And so this is some work that we did in this system where we downscaled only 3 of the 73 ensemble members because it is so expensive to downscale. But we dropped down to kind of 0.1 or roughly 10 kilometre spatial resolution. You can kind of see that huge improvement in the resolution of sea surface temperature. Okay, so working with these downscale forecasts, we reran those forecasts for the whale kind of compression index, and we wanted to compare the two. So this is kind of trying to get at this question of, do we need to downscale given it is so expensive in order to do that, and what's the kind of added benefit? So here we have the correlation coefficient of the compression index of the global model with all 73 ensemble members. This is the exact same information that I've already shown. I've just kind of put it into a box plot form. And so when we consider, if we're only looking at the 3 ensemble members that we downscaled, but keeping it only at the global resolution, the course resolution of 1 degree, we have a big drop in skill. So this is kind of the correlation coefficients getting worse overall. But when we downscale those 3 ensemble members, we get an improvement in skill. But that improvement of downscaling isn't enough to actually outcompete the benefits of using 73 ensemble members. And so this is this kind of trade-off here of downscaling is really great, and it helps improve the skill from the global model. But because downscaling is so expensive and you usually have to subset your model, it doesn't actually outweigh the improvement of using these 73 ensemble members. So kind of in a perfect world, we'd dynamically downscale all 73 ensemble members, but that just really isn't feasible. Okay, and so that was for one metric, the correlation coefficients, but that relationship still holds when we look at forecast accuracy and SETI, this kind of curved shape here, where the global 73 ensemble member models typically have the best skill. Okay, so from that, we were, I guess, generally encouraged by that, but conscious that the 2 case studies that I tested it on, the whales and the turtle kind of case studies, they are regionally specific. And so we wanted to kind of develop this guide for practitioners that's hopefully a little bit more useful in terms of, should you downscale, should you wait for downscaling to happen? And what are the kind of added benefits of staying at the global level versus moving to the downscaled level? And that really just depends on your preference, what space you're working in, what kind of ecological forecast you're wanting to develop. So for example, the global forecasts, don't have biogeochemical variables readily available. And if they're not important for you, then it doesn't matter. But in some systems, if you're wanting to actually look at oxygen or productivity, then you would actually need to downscale and kind of couple that with a biogeochemical model. I think one of the big ones for me that I think a big trade-off is actually making tools operational, so that you can kind of serve them operationally to an end user. Now, those global forecast or sea surface temperature forecasts are already operational on the North American multi-model ensemble, but the downscaled ones actually requires a whole need to build and maintain those operational forecasts, which is a huge barrier because it is incredibly difficult to maintain operational products. There's also lots of trade-offs in terms of the spatial and temporal resolution that you're wanting to work at. Obviously, downscaling is giving you a much finer resolution in both space and time. And I think one of the big ones that I think is really important to talk about is actually the accessibility. So, in the ecological forecasting initiative, OEFI, that we're part of, a huge reason for that kind of grassroots movement was to actually expand the community and start teaching and learning about forecasting and making it part of the kind of curriculum for science moving forward. But working with operational outputs and forecast outputs are very difficult. And if you can kind of have those already served online in an operational context, that kind of enables ecological forecasters to kind of go ahead and start using them. You don't have to wait for downscaling to be conducted for your region. You already have the tools ready to go ahead and use those outputs. And that is also the accessibility component when you move to the kind of computational limits and storage limits of, if someone else at another organization is already serving these outputs, you just have to pull them down from a website. That's incredibly powerful. And I think it really opens the door for moving or expanding the field of ecological forecasting much more rapidly. without kind of having to wait for downscaling to occur. Or if you don't have the resources, then you can kind of go ahead and start already. So I think on that, I'll wrap up a little bit. So in summary, I kind of just showed that there's a huge capacity for existing tools that we already have to transition to a forecast configuration. That ecological forecasts can forewarn of human-wildlife interactions, and especially during climate extremes that we're starting to see much more commonly around the world. And finally, don't wait for regional downscaling to occur in your region. You can charge ahead right now, working with global forecasts that are already operational. And so with that, I'd like to thank all my co-authors that are shown here at the bottom of the screen, and I'll take any questions and have a discussion. And I'm just going to stop sharing my slides so I can see people's faces.
Thanks, Steph. That was really, really good. Are there any questions? Belinda?
Yep. Hi, Steph. That was fantastic. Amazing work. I'm so impressed by how well the forecasts work that far out. Like, I was quite surprised that you could forecast reliably 12 months out. What's your secret? What is it that makes it possible to be able to forecast, given that, I mean, the weather forecasts aren't that good. So how does that work?
Yeah, no, it's a great question. And I was also surprised, very happily surprised by the results. And what it's really pointing to is actually more of kind of like low frequency variability in the system. Like, these management tools are actually quite large averages of ocean conditions. And so you're kind of smoothing out a lot of the noise in the system, and you're just kind of generally trying to predict anomalies. So it's not like an anomaly of one single grid cell, but anomalies of a rather large region. And that's, I think, where we're kind of getting that increased forecast lead time from, because we're not just looking at a single grid cell and seeing how well could we predict an anomaly in a grid cell.
Thanks. Nicholas?
Thank you. Thanks, Steph. That was a really nice talk. Really enjoyed it. I just had a question about that sort of compression that happens with the whale example that you mentioned. So is it always the case where the cold water gets kind of compressed up against the coast, or does the hot water occur near the coast and the cold water occurs sort of offshore, or how does that work?
Typically, no, because California is very much an upwelling system. And so inherent in upwelling, you kind of have these surface waters that get pushed offshore, which draws up the cool, nutrient-rich, kind of oxygen-poor water from the ocean depths, and that kind of comes up against the coast. And so you wouldn't ever get kind of like the inverse, but rather the area of that upwelling can change, and the kind of quality of that upwelling can change seasonally, it can change between years. It's quite variable. So it was a really cool metric in the sense that in an upwelling system, it's very dynamic, but here was just like a simple sea surface temperature kind of ratio between inshore and offshore waters, and that was enough to kind of show how much whales can kind of compress against the coast.
Yeah, right. Okay. So I just have a small follow-up question on that. Does it ever happen where it's kind of more fragmented in some years than others? Like the area itself is kind of important, but also how fragmented those cold waters are.
Yeah, definitely. There's certain areas, and there's certain areas that are better than others in terms of like good upwelling habitat, but you also see that in whale distributions too, that in certain years there'll be, wonderful foraging in one particular area or one canyon where whales will be, and that kind of predictability of whale distribution is quite challenging, and there's a lot of people kind of working in that space. But in terms of just general foraging habitat that's available to whales can be simply predicted by how much upwelled water there is. And so when the forecast that I showed was actually just for maybe I think it only spans 2 management zones, but I could expand it along the much larger kind of entire west coast of the US across the kind of entire upwelling zone, which is 6 management zones. And I think we would actually start to see a bit more of that patchiness and variability between the different zones. That'll be future work, I think.
Sure. No, that sounds great. Thank you very much.
Thanks.
Lisa?
Hi, Steph. Yeah, thank you for the talk. I wanted to know if there was any particular reasons you picked those 2 tools to do this forecasting research on, and also the other ones. Do you see any maybe problems with a few tools that you can't do forecasting with? Could you, elaborate on that a little bit?
Yeah, so we picked the 2 tools that we think were going to give us the best skill. Obviously, like, we're not going to pick a tool that we know is going to fail. And I think what that came down to was a number of different factors. One was that these management tools only relied on temperature, and temperature kind of averaged and chopped into different bits and pieces, but it was still only temperature. So the next, a lot of the tools that we do have take it one step further, where we might have an ecological model that has multiple variables and kind of non-linearity of species responses to those variables all kind of integrated into it. And trying to predict that with forecast variables just inherently decreases your skill. That right off the bat, it doesn't matter how good each of those models are, just multiplying the 2 together, you're just going to get decreased skill. So that was kind of initially where we wanted to test it, but we had some serious concerns about some of the variables of interest, the physical variables and their skill. So we knew that we had really good skill with ocean temperature, but less so with something like mixed layer depth. And so we, right off the bat knew we couldn't use a few tools. There wasn't kind of any point in testing them. But in one of the tools there, I think was a sardine kind of spawning habitat, which is based off temperature and informing surveys. And so I think that could be like a next potential tool that we might want to test. Yeah. Does that kind of get at your question a little bit?
Yeah, makes perfect sense. Thank you so much.
David? Put his hand down. Belinda?
I think you're on mute.
How long have we been on Zoom? Great talk, Steph. It was great to see all the little bits and pieces. I've seen little bits and pieces of this in various fora. It's really great to see it all stuck together so coherently. A kind of simple question. Were your downscaled and global models on the same temporal scale? Because in your table, you said that the global models were more or less monthly, but the downscaled was daily. Does that have an effect on your correlations?
Yes. Yeah, good point. So on one of the slides I showed the skill assessment, it was daily of the physical variables. That's kind of work that Mike Jaycox has in review. But when I actually did it for my stuff in terms of the 2 management tools, I averaged the downscaled output to be monthly. Okay. So I kind of, I tried to account for that.
You're comparing apples with apples, because I was just wondering if it wasn't just extra noise added by daily variables rather than monthly, whereas monthly you might get a sort of broader picture.
Yeah, exactly. Yeah. And I think there would be something in that, I think, if I did do that comparison of daily to monthly, but I think it would still get kind of averaged out a little bit as we average those metrics over such kind of coarse spatial and temporal scales as well.
Yeah.
And that it also kind of matches, and this is maybe getting back to Lisa's question a little bit of the tools that we used were served on a monthly average, but that relates to the kind of movements of these highly migratory species. We're trying to predict movements on a daily scale is very, very difficult, but trying to predict them on a monthly scale is a lot easier of a whale that's going to migrate through an area during a certain season. So there's that kind of element to why we have increased predictive skill too. Sorry, that was probably coming back to Belinda's question.
Yeah, and seeing as Nicholas took an extra follow-on, I'm going to take a follow-on too. Sorry. Do you think we have a realistic hope of getting sort of decent forecasts, given that even the models that we base in the forecasts on really only have skill for temperature, and then mainly only for sea surface temperature? I mean, how close are we to actually having the data that we can base skillful forecasts on?
Oh, yeah. I'm gonna have the cop out
probably
answer.
an unfair
I'm
question.
the ecologist. I use the outputs of the physical modelers. I think we'll get there, and I think we'll get there sooner than we've gotten to this point, if that makes sense.
Yeah.
Temperature is incredibly powerful as a predictor of ecology. And so it's nice that we have that, at least, of all the variables that we could have picked, we want temperature.
I must remember to pick you as a reviewer for papers, because every time I write a paper mainly about temperature, they go, "What about everything else?" You go, "Like, we don't know anything about everything else." But they always ask.
Yeah, I mean, that's always it actually also points to the importance of having ecologists and physical modelers talking to each other, because not everyone knows that the variables that ecologists care about, and I think that's often a conversation and a point that we really need to push, of just like, these are the top 5 variables that we want out of your models, like please store these outputs at these spatial and temporal scales because we'll use them.
We actually had that discussion ahead of the IPCC 6th assessment report. There was an expert data meeting, and we asked for variables to be stored, and it made no difference.
Okay. Yeah, maybe if we beat the drum loud enough, someone will listen.
Okay, I'll shut up now.
Thanks, David. Belinda?
Yeah, I didn't get my second follow-up last time, so I'm coming back again. So can I ask you, Steph, to talk a little bit more about extremes? You mentioned that you were using an extreme index. And so I just wanted to hear a bit more about, how do extremes come into it? Like, how does it depend on the extreme values, and how are you handling those extremes?
Good question. So I'm not inherently specifying extremes, but rather I'm kind of, for every month of every year, I'm developing these forecasts. And when you kind of look at the long-term time series of that, then you kind of you can identify what are the anomalous conditions. And so for a few of the years where we know a marine heat wave has come through and, caused chaos in the system, I've just picked out those years and said, okay, in 2015, we had a huge marine heat wave. How did our forecast go? Like, could we predict it at all? And so that was more, I guess, just drawing or focusing on a certain point that I know is relevant. It wasn't part of the analysis. Like, we generated forecasts for the entire time period, including normal conditions. But, like, if we only ever had normal conditions, we could just have a climatology and we would have perfect skill, if nothing ever changed. So the idea of forecasts and kind of an ecological forecast is trying to inherently predict those anomalous events, I should say, and those extremes. So it's, I'm not sure if that's answering your question at all.
Yeah. So I guess when I hear extremes, I think you mean like not just anomalies, but kind of the extreme anomalies, which is something that so I'm a plant ecologist thinking about mortality all the time. So it's really like the lowest percentile of rainfall, for example, that drives what you see in the ecosystem. So I'm thinking about like real extreme values as opposed to anomalies. And now I'm just kind of going, are you using extreme in a slightly different sense than I am? Yes. Or
I think so. So yeah. When we kind of the forecast accuracy metric, where we convert a forecast into that confusion matrix, the thresholds of where that confusion matrix intersects, I'm going to get that wrong, changes depending on the tool. So habitat compression adds any value below the mean. And so an extreme happens 50% of the time.
Yeah, right. Yep. Yeah, okay.
The median, I should say. But for the turtles, the threshold was kind of was determined on past loggerhead bycatch events. And so that was kind of a whole separate analysis that said at the, what was it? Sea surface temperature anomalies of 0.7, which is maybe the 70th percentile, was considered extreme. And so it really just depends on the management context. And we kind of see that, it depends on the management tool as to what we set as those thresholds. But it is really important to communicate that, because, a correlation coefficient is, oh yeah, great, you got a high correlation. But to an end user or a manager who's saying is this event going to happen or not? They want that binary answer. Then converting that to that confusion matrix is really helpful, or that, kind of calculating the true positive rates. And so, the thresholds on that will depend on the tool.
Yep, cool. Thank you.
Thanks, Belinda. Jessica?
Hey, that was really cool. I just had a quick question. How much does it cost to downscale one ensemble member?
It's costly in many ways, right? So, I mean, some much cleverer people than I wrote a really great proposal to downscale it, but it took, a researcher a really long time. It required a lot of computational, equipment and storage and power to run it. And even then, and I didn't get into this, it was so expensive that we only stored the output of 2 initialization dates. So instead of, running it an initialization date 12 times a year, like at the start of every month, we only did it twice, once in January, once in July. And I made sure it was like an apples to apples comparison. But that's kind of like the sheer amount of data that kind of was generated. And it was for 1980 to 2010. So I can't give you a number, but that it's difficult. And, it also required, the person with the skills to do it was a postdoc. So how many years of training does it take to get to, to train someone up with the skill set to be able to even do it? It's kind of expensive in that way.
Yeah, wow, thanks.
Yeah. And, in that saying, I have no idea how to downscale. Absolutely no idea.
But then you showed us that person wasted their entire grant and time anyway, because he could just use the models, the global models.
Yeah. Well, but, what was interesting, and I think what was really important, was that downscaling does improve skill beyond the global models for those, 3 that we tested. So if we had infinite power and resources, we could downscale it all on an operational, scale. So one day.
Awesome. Thank you.
So, if there are no more questions, I did have one, and it's a bit different. I hope it's not putting you on the spot, and if it is, don't worry about it. You don't need to answer it. But I was really impressed by all the different scales of forecasting that you were talking about in marine science. And it seems like so much has been done, and including your great work. Where to next?
Good question. So I love working in this space. I worked in this space for a while. I first developed a forecast during my PhD in ecological forecast, which was a steep learning curve, but it certainly got me into the area. So I've started a research position at CSIRO. So I'm hoping to continue some of the work in this space because I am interested and passionate about it. And I think it's also needed, you know, like the extremes that we're kind of seeing around the world are quite shocking. Like we're moving into a whole new space that we at the moment are not prepared for. And I think having these forecasts and more forecasts that end users are using are going to be key. But I think that's the big challenge is developing a tool that's skillful, that someone can use, that kind of emphasis on the stakeholder and use, I think is a huge barrier.
Yeah, I really like that idea. Focusing on the stakeholder keeps you relevant and could be really exciting. So thank you.